Welcome to Summarize Science. Imagine a robot that can be shipped as a flat sheet of paper and then fold itself into a complex machine on demand. This is the promise of origami-inspired robotics, but turning a simple crease pattern into a functional machine is incredibly difficult. Traditionally, designing these robots involves a slow and expensive process of physical trial and error. To solve this, a team of researchers has developed a powerful new framework to design and test origami robots entirely within a computer simulation. Their system starts with an intuitive graphical interface where a user can draw the vertices and creases of their design. This 2D blueprint is then automatically converted into a dynamic 3D model inside a high-fidelity physics simulator called MuJoCo. This allows designers to see how their creations will move, bend, and interact with objects in a realistic virtual world. The framework is versatile enough to model all sorts of mechanisms, from a gripper that can grasp objects to a legged robot that can walk and even balance a rolling sphere. This digital sandbox lets engineers rapidly test ideas that would take days or weeks to build physically. To truly put their system to the test, the researchers focused on one specific challenge: creating the ultimate origami catapult. The goal was simple: optimize the catapult's geometry to throw a small projectile as far as possible. They identified two key design parameters to tweak: the sharpness of the main fold angle and the length of the throwing arm. Instead of guessing the best combination, they used a sophisticated optimization algorithm to do the hard work. This algorithm, called CMAS, started with random designs and intelligently evolved them over 200 virtual generations. As you can see in this heat map, the algorithm efficiently explored the possibilities, quickly ignoring bad designs and converging on a high-performance sweet spot. It automatically discovered the optimal arm length and fold angle for maximum throwing distance. With the perfect design found in simulation, the next step was to see if it worked in the real world. The team 3D printed 3 different versions of the catapult. They printed the randomly generated initial design, an improved design from the 8th generation of the simulation, and the final, fully optimized design. The results were a resounding success. Just as the simulation predicted, the final optimized design consistently threw the projectile the farthest. The initial design had the shortest throws, and the 8th generation design was right in the middle, perfectly matching the performance ranking predicted by the computer. While the absolute throwing distances were different between simulation and reality due to factors like air resistance and material imperfections, the relative performance was spot on. This proves the simulation is an incredibly reliable tool for comparative design and finding the best possible geometry for a task. So, to recap, these researchers created a complete pipeline to go from a simple 2D drawing to an optimized, functional origami robot. Their simulation-driven approach allows for rapid design and optimization without needing to build constant physical prototypes. They validated their digital results with real-world experiments, proving the power and accuracy of their method. Frameworks like this could dramatically accelerate the development of next-generation origami robots for everything from minimally invasive surgery to deployable structures in space.